Hello, students. Having solved the two-body problem for a massless orbit around a mass, let's solve for two massive bodies. Let's solve the problem for barycentric orbits. Let's consider this arrangement here with the origin O, and the central mass is at the point O prime. The central mass of masses M1 and M2. Drawing here are the position vectors of the different masses. So R, big R, is the position vector of the central mass O prime. And the position of the central mass is defined by the equation M1R1 plus M2R2 over the sum of the masses. Now, the masses and the central mass, they lie on a straight line. So if you write that the vector big R1 is equal to little r1 minus big R, and that R2 is equal to little r2 minus big R, if we substitute little r1 and little r2 on the equation for the position vector big R, then we see that the terms involving big R will cancel out. Then we have the M1 times big R1 plus M2 times big R2 is equal to 0. So this implies that R1 is always in the opposite direction to R2, and therefore that the central mass is always on a line that is joining M1 and M2. So you can see indeed, this is what is shown in the figure. R1 and R2 are in the same line and pointing in opposite directions. So we can write, abandoning the vector notation, that the modulus of R1 and R2 sum up to the separation between the objects, call it little r. And the distances of the masses from the central mass are related by M1 times R1 is equal to M2 times R2. Thus, it follows from these definitions that the modulus R1 of the vector R1 is equal to M2 over M1 plus M2 times the separation, and R2 is equal to M1 of time over M1 plus M2 times the separation. As you see, big R1 and big R2 are just scaled versions of the separation little r. Therefore, whatever the conic section is describing the relative motion of the two masses, each mass will also orbit the central mass of the system in a path described by the same conic section, reduced in scale by either M1 over the sum of the masses or by M2 over the sum of the masses. This is shown here in these figures. In figure A, you have a system that is centered on the mass M1 and showing the motion of the mass M2 and of the central mass, the little dashed ellipse around the mass M1. You can shift the coordinate system now to the central mass, and then in this system, the mass M2 is executing this larger elliptical orbit around the central mass, and the mass M1 is executing a similar ellipse around the central mass. A coordinate system referred to the central mass is called a barycentric system. This is an example of barycentric orbits. You're seeing here the cross marks the central mass, and the two bodies, in this case of equal mass, execute identical ellipses but mirrored around the central mass. This is seen also here on this approach of the New Horizons to the Pluto system. You see Pluto and Charon orbiting around their common central mass. So you can see from this that even though the two bodies have their orbits around the central mass, these orbits are not independent. They are going around with the same mean motion, with the same period. So to understand that, let's look at the angular momentum. From the motion of M2 around M1, consider it occurs with an angular momentum equal to r squared times theta dot. And that is a constant, where r is the separation between the bodies. Now, because the radius vectors between the central mass and the bodies is a function of the separation, then it follows that you can define all two quantities, L1, which is equal to r1 squared theta dot, and L2 equal to R2 squared theta dot. And because R1 and R2 are functions of the separation, they also have to be constant. Now, if you multiply L1 by M1 and M2 by L2, you have the total angular momentum of the system. Call it L star. Now, this sum is equal to M1 times M2 over the sum of the masses times the constant angular momentum per mass of M2 around M1. Now you can invert that to find L in terms of L star. Again, remember, L is the angular momentum per mass and L star the angular momentum. Now, because L is a constant, the motion occurs with a period given by theta dot. And the two orbits also happen with the same period. So you can say that their mean motions are the same. I used the Keplerian frequency before, but let's call it now mean motion. The mean motion is n equal to 2 pi over the period. It's better to call it n instead of omega. Omega would be the instantaneous Keplerian frequency, which is theta dot. So the mean motion of the orbits are the same. Now the semi-major axes of the orbits are derived from the relation for the radius vector. If you substitute this for a circular orbit, the r's become semi-major axes. Now let's find the angular momentum of the orbits L1 and L2. And remember the relation between eccentricity and angular momentum, and the relationship for the energy and the semi-major axis. If you substitute this energy into the angular momentum, you have that the angular momentum is the square root of mu a times 1 minus z squared. Now mu is equal to gm. So you can write mu in terms of the mean motion. The mean motion being 2 pi over period. If you use Kepler's third law, this is equal to the square root of gm over a cubed. Since gm is equal to mu, then you can write that mu is equal to n squared times a cubed. You substitute that in the angular momentum, then you have the angular momentum is equal to na squared times the square root of 1 minus z squared. Now, if you substitute this equation for the angular momentum in the equation for the angular momentum of the individual orbits, where this is the semi-major axis of the orbit of M2 around M1 and the eccentricity of the orbit of M2 around M1. But from the equation we found for the semi-major axis, we can substitute this by the semi-major axis square of the individual orbits. By symmetry with this equation, we concluded that the eccentricity of the individual orbits have to be identical. Although each mass moves on its own elliptical orbit with respect to the common central mass, the pericenters of their orbits differ by pi. This is what we saw here. These orbits have pericenter and apocenter at the same time, but their arguments of pericenter differ by 180 degrees. Let's now look at the energies of the orbit. If you consider the total energy of the system, not per mass, but the total energy, this is going to be the sum of the kinetic energy of the first body plus the kinetic energy of the second body minus the gravitational potential energy binding the system. And this has to be identical to minus g times m1, m2 over twice the semi-major axis of the orbit of m2 around m1. So let's write the velocities in terms of cylindrical coordinates and write the energy in terms of radius and azimuth. Now, if you write R1 and R2 in terms of the separation, R dot square plus R square theta dot square over 2 is a kinetic energy per mass of the orbit of M2 around M1. So you can write this in terms of E star is equal to M1 times M2 over the sum of the masses times the energy per mass of the orbit of M2 around M1. Again, you can write the energy per mass in terms of the total energy by inverting this equation. Now notice that because the energy per mass of the orbit of M1 around M2 depends only on the semi-major axis of that orbit, then again, the total energy depends only on the semi-major axis of the orbit of M2 around M1, as indeed we expected.